In today's video, we'll discuss about trapezoidal method and how it is used to find area under the curve, or you can say definite integrals numerically, which are very hard to solve analytically. Let's start with an easy diagram. This is y-axis, this is x-axis, and let's say you have a curve something like this, and let's call it fx, and you want to find area under this curve from point A to say point B. Okay, now what does trapezoidal rule says? For this range, you can divide this portion into many trapezoids. Let's take a case when we divide this entire region into two portions. Let's take this. Now this becomes one trapezoid and this becomes another trapezoid. For generalization purposes, we will call this point x0, this is x1, and let's call last point xn, not x2, because soon you will realize that when we generalize it is easier for us to do it this way. Also this point becomes fa, fx1 and fxn. fxn, fx1. Now what trapezoidal rule says that when we have to find area under this curve from A to B, fx dx, it is approximately equal to sum of these two trapezoids, which means let's call this one I and this I2. So area of I plus area of this second trapezoid. Now let's think about areas of these trapezoids. Area of trapezoid is given by half into sum of these parallel lines, this one and this one. Now length of this line is fa1 or fx naught, so let's write it like this, fx naught plus length of this one is fx1 times the distance between them, the difference between two parallel lines, which is given by this x1 minus x naught. This is the area of this first trapezoid. For second trapezoid, we'll add the area of other one into this. It will become fx1 plus fxn times xn minus x1. Basically this is all you have to do, but here as we can see that this area under the curve is not exactly equal to area of these two trapezoids. This area is not being counted when we are doing it for just two of them. So what we can do is we can increase these number of trapezoids to very large number so that this trapezoids becomes very small, such that this area almost vanishes and our approximation becomes much better, and we tend to the exact value of definite integral or area under the curve. So how to do that? Let's say in this case we divided our portion into two intervals, so n for our case was 2. So let's define a parameter a is equal to b minus a by 2, or n, say n. For our case it is xn minus x naught divided by 2. So h is basically this h. This height is h, xn minus this and half. These lengths are equal, okay, h and h. Now what can we do? Um, let's start with this case and we'll see how we can generalize it. Okay, from here we can see that this area x1 minus x naught, see, x1 minus x naught, x1 minus x naught is equal to h, is equal to h. So we can put an h here, and similarly xn minus x1 is also h, so we can put an h here. You can see there is an h by 2 term common from here, and we will get fx naught plus fx1 plus fx1 plus fxn. You may write it like this: fx naught plus fxn plus 2 times f of x1. This, what we have done is for the case of n is equal to 2. Now, is there a way we can generalize it for, let's say, when n is a very large number? The answer is yes, we can do that. How to do it? Let's think it like this. When we divide this into large number of portions like this, we need to generalize things like this. These points x0 and x1 should be written like x0 is equal to a. Okay, this point x0 is equal to a, x1 will be equal to a plus this length, a plus h, x2 will be equal to x1 plus h, or a plus h plus h, just like this. X1 from here, a plus h plus h, so a plus 2h. So if I have to generalize it, I can write it like a I xi is equal to a plus 2 a plus ih. This is an important relation we'll be using soon. And for xn1, n is basically the last digit, so xn is equal to a plus hn. Okay, this is the relation which will give us the value of xi, that is any point on this range xi will can be calculated using just a and I values, a, I and h values. Okay, now how can we generalize this? For n cases, these results are for the endpoints, so they will remain the same. Let me write for general case, that is large n value. So our area can be approximated by h by 2 fx naught plus fxn. Fxn here is the last value or b. Okay, this is just b, this is h, x naught is a. Now this is important thing. Since when we calculated it for two regions, we have one coinciding point, one for this trapezoid and second for this trapezoid. Similarly, for for in this case for two trapezoids we had one line which was coinciding this. So for n number of intervals we'll be having n minus 1 intersecting lines. So we'll be summing it over I is equal to 1 to n minus 1 and not n, as we got it here. Similarly, we will generalize it like this, because when there are many points we'll have to sum them over. We are summing it from here, so x I, summation from I is equal to 1 to n minus 1. I is equal to 1 means fx1. Okay, x naught we have already taken the first point, fx1 will be the second point just next to it, x1 will be x naught plus h. Okay, uh, yes, everything is fine. Fxi is giving the general value of any point lying in this range from I is equal to 1 to n minus 1, n minus 1 not n, because for two trapezoids only one line is coinciding, for three trapezoids two line will be coinciding, and for those coinciding lines this fxi accounts for them, that's why n minus 1. You can see it for yourself. So basically this is our approximation. I can write it more spacious if you cannot see it properly. It is approximated by h over 2 fx naught plus fxn plus 2 times summation of n minus 1 I is equal to 1 fxi, where h is equal to xn minus x naught over n. Here we divided it into two intervals, and when we divide it into n intervals, then this is the value of h. Now I have calculated value of a very simple integral just to show you how this method works. Let's rub this portion. First let's calculate, let's take x squared, very simple function, from 1 to 2 just for simplicity. You can take complex functions which are hard to solve by hand analytically and then try this method. So for x square we have x cube over 3 from 2 to 1. So 1 by 3, 2 to the power 3 minus 1 to the power 2, or 3, yes, 3 minus 1 to the power 3. So 8 minus 1 by 3, 7 by 3. 7 by 3 is approximately 2.33 and 3, something like that. It keeps on going. Let me just verify with the calculator. 7 by 3, yes, 2.33. Now applying trapezoidal rule, what we should get from 1 to 2 x square dx will be approximately, let's apply this, let's take n n is equal to 5 firstly. So our h value becomes 2 minus 1 over 5, which is 1 by 5 or 0.2. So this becomes 0.2 divided by 2, which is 0.1 times value of x squared at 1, which is 1, plus value of x squared at 2, which is 2 squared, which is 4, plus 2 times summation I is equal to 1 to n minus 1, 4 in this case, and xi squared. Here xi, for xi you have to use this relation, so basically write it like this: xi is equal to a plus ih. A here is 1 and h here is 0.2, so 1 plus 0.2 times x or I, let's say I in this case, I squared. Fine. And you can calculate it using a calculator. You will get the value approximately 2.34. This is for n is equal to 5. When you calculate it for n is equal to, let's say, 50, when you keep increasing the value of n, the answer becomes more and more accurate. You will get the value around 2.3334, something like that, which basically shows that for large value of n, this function is becoming more and more accurate. You can try it for various types of functions. Let's say this type of functions, x, sin x, or very complicated looking functions, a to b, 10x over x squared, sin x over x, and so on. Any type of functions. So it was the basic idea of how to generalize trapezoidal method for different type of functions. Basically you have to keep this in mind, and don't forget that xi is equal to a plus ih from here. Thank you.